So we have previously defined Reynolds transport theorem to be a theorem that gives us conservation laws that are applied for systems and upgrades them to give us conservation laws for control volumes. So if we have a property B for a system, we use Reynolds transport theorem in order to obtain a conservation law for the same property in a control volume. As an example of that, I'm going to start with a study of the conservation of mass. So we know that we can apply the conservation of mass law from a system to a control volume. We know that for a system, if B system is basically the mass, then by definition, dB by dt becomes dm by dt for a system, and this is basically equal to 0 by definition because a system is defined as a quantity of matter, and thus this quantity has to be fixed. And if we actually just substitute this into Reynolds transport theorem, which we have up here, first of all, capital B is the mass of our system, like we said, and then small b, which is the intensive property corresponding to the mass, is going to be m over m, which is just 1. So substituting this into Reynolds transport equation gives us 0 equals d by dt integral of cv rho times 1 for small b dv plus an integral over the control surface times rho vr dot n dA. This is our conservation law for a control volume for the mass. Now, what do the different terms in this conservation law tell us? If we look at the terms we have, our first term represents the unsteady term. This is basically the variation of the mass within the control volume. So we can also write this as dmcv by dt actually. And our second term represents the net mass flow rate out of the control volume. And basically the mass flow is going to essentially happen at the surfaces of our control volume, and that's why our integral here is over the control surface. So basically this is the net mass flow rate out of the control volume through the control surfaces of this control volume. Now we can do two simple simplifications. In case we have a steady flow, then essentially this term cancels out to 0. Whereas we can do a second simplification if we have well-defined inlets and outlets. In that situation, we can split the integral of the net flow rate of the mass into the different inlets and outlets that we have. So let's suppose my control volume contains these 2 inlets and 2 outlets. Then I can simply write down this integral into the sum of the inlets and the outlets flow rates. So the integral of rho vr dot n dA is going to be equal to the sum of the mass flow rate into the control volume plus the mass flow rate out. I have a minus sign here because what's out minus what's in will give me the net flow rate out of the control volume through the control surfaces. So I can now substitute this integral by these two terms. Let's check an example. So I have a problem here which we can solve. On the formula of the conservation of mass for a control volume. So here basically I have a rigid tank of volume V, and the mass flow rate of the air entering the tank is constant and given. Air is being pumped into this tank, and we assume that we have a constant temperature, and we want to generate an equation for the density rho in the tank as a function of time. We're trying to find an expression for rho. Now, since I have this constant mass flow rate, due to this flow of the mass, the density in here is essentially going to increase. Now, to study the effect of mass on the density, let's study our conservation of mass equation for an appropriate control volume corresponding to this situation. Obviously, our control volume must contain this whole tank along with the inlet through which the air is being pumped, right? So the conservation of mass equation, we found it previously. It says that we have an unsteady term over the control volume plus the term which gives us the net flow rate into our control volume, which was written as rho v dot n dv. Now these two should be equal to 0. This is the conservation of mass equation for a control volume. Now we just discussed that we can substitute this integral by a sum of the mass flow rates over the well-defined inlets and outlets. If we look at our system here, we can clearly see that we have only just one inlet. So we do have well-defined inlets, and thus this integral can be written as the sum of m in dot plus the sum of the outflow. We have a minus sign here again. And we can see, we can leave this here. By the way, this is obviously not a steady flow because I can see that the mass flow is going to affect the volume here everywhere, the speed here everywhere, and thus I do have an increase in the mass of the control volume with time. And we said that this term represents the variation of the mass within the control volume with respect to time. So this is obviously an unsteady flow, and this term will not actually cancel out. We can see that for our defined inlets and outlets, I only have one inlet, we have no outlets, so now our equation is going to be reduced furthermore. So I will have now d by dt integral over the control volume of rho dv minus, I only have one inlet, so I can just write this as m dot n for the one inlet that I have. Now let's see how we can further simplify our equation. I'm going to assume that rho depends on time only. And this assumption is completely valid because if you look at our situation here, air is being pumped into this tank, and I can totally assume that the density here is the same everywhere with respect to position. It's not varying at different locations. It's only varying with time as more and more mass is pumped into this tank. So the density is actually increasing uniformly everywhere with time. So rho depends on time only. It is uniform everywhere, which means it's independent of position, which means that I can simply take it outside my integral, which is over the volume. And this will basically be just the volume, which is the volume of my control volume. I can write this as capital V, and now I get d rho by dt of V minus m dot n is equal to 0. I can rearrange this. I will get d rho by dt equals m dot n over V, which is equal to a constant. I can just now resolve d rho to one side and m dot n over v with dt to the other side. Now these two terms are constant, so if I integrate both sides, these will stay outside, and I will obtain an integral of d rho from rho 0, which is the initial density at t equals 0 as given in my figure, rho equals rho 0 at t equals 0, to rho, which is the density at any instant time, and this is going to be the integral from t equals 0 to any instant t, and this will give us rho minus rho 0 equals mn dot over v times time. And I have just obtained an equation of the density as a function of time. It will be rho 0 plus m dot n over v times t. You can see how my density is a linear function of time, and this makes sense because if you look at our flow rate, it is constant with time. So the mass entering this tank, the mass of air entering this tank, is increasing linearly with time because of this constant flow rate, which would lead to a linear increase in the density inside this tank as well.